Hello and welcome to this webinar with the title Discovering the Geometric Suite of Data Analytics Solutions. This webinar is number 4 in a series of 11 webinars aimed at exploiting the properties of the Geometrics Suite. The subtitle of today's presentation is The Basics of Data Analytics. Some of you may have attended the earlier webinars in this series, so then this slide is familiar to you, but I will still review the elements making up the geometric suite. So first of all, we have the MODES software for design of experiments and quality by design, in short, to get the data right from start. The second element in the geometric suite is the Easy Analytics solution for enabling everyday data-driven decisions in an efficient way. The third element is the SIMCA offline solution for multivariate data analysis. The fourth ingredient is the SIMCA online solution for deploying models developed in SIMCA offline in a real-time setting. And then we have the complementary tools Control Advisor and Active Dashboard for enabling advanced forecast and advanced overview. This webinar is number 4 in the series of 11, as I said, and today we're going to look into the properties of the SIMCA software and get familiar with what we call multivariate data analysis. Just another little review. Webinar number 1 and 2 in this series were looking into MODE, and if you have not watched those webinars, they are accessible as recordings. And the third webinar that we just performed looks into the capabilities of Easy Analytics, and that webinar is also available as a recording. And today we're opening the secret doors into, we are opening the doors into the secrecies of the SIMCA software, you can say, and we're going to walk through SIMCA in the next couple of webinars. Here we have a little outline of today's presentation. We have an introduction. We are going to describe what multivariate data analysis is using simple analogies to common data terms that are used today. We are going to apply multivariate data analysis to the betting odds of winning the Premier League in the UK, who will win the Premiership according to the betting firms. And then we will also apply MVDA on a perhaps more industrially relevant application, dealing with characterization of properties of raw material coming into a pharmaceutical company. We will also demonstrate both of these two data sets using the SIMCA software, and after the demo there will be some summary and conclusions, and towards the end there will be a Q&A session. So as an introduction to this topic, we can say that we are right now witnessing a data explosion. There are more data than ever measured in our society and industrial sectors. One very interesting estimate comes from the organization UNECE, United Nations Economic Commission on Europe, that in late 2015 estimated that within 4 years the amount of available data is expected to treble. So there is no doubt that data is everywhere, from the production floor to your local grocery store and Facebook. So it might be quite easy to get the impression that we find ourselves trapped in a numerical jungle without sense of direction in which to move for improving our situation. Now, fortunately, the geometric suite contains the powerful SIMCA software for multivariate data analysis, and in the next couple of webinars I will show you how you can extract value from data by applying the data analytical workhorses residing inside the SIMCA software to your data, both data residing in your historical databases and data that you're going to generate in a smart way in the future. So then, what is MVDA? Well, one way to say that what MVDA is that it will estimate summary variables. And you may then question, what is a summary variable? Well, I think that one of the summary variables that you may already have come across is a stock index. In the line chart here, we see how the stock index of the Dow Jones is changing as a function of time in a 48-hour time period in August 2013. Dow Jones index is monitored by investors, and depending on how this summary index is migrating up and down over time, the investors may decide on different actions. They may sell, they may buy, or whatever. Um, and the Dow Jones index is no more than a summary information of the stock markets or stocks of the individual companies weighted together using some weighting function. In process modeling using multivariate data analysis inside the SIMCA software, we are doing something very similar. Conceptually, it is very similar, at least. And that is that we are calculating summary indices of how the process is performing. And this summary can apply to a continuous process, to a batch process, or hybrids thereof, and to any other type of data table, not necessarily containing process production data. The common thing with the Dow Jones index is that the process summary index is some trend over time that you will monitor and value how it is going up and down. And you may decide if you're a process engineer or a process operator on various actions, or perhaps refrain from actions depending on how this summary index looks across time. The little difference is that usually in a trend chart like this, when you're dealing with process data, you will reference the performance or the trajectory of the summary index in relation to lower and upper limits, usually positioned at plus and minus 2 standard deviations, where you have perhaps warning limits, and then action limits at plus and minus 3 standard deviations. So the basic message so far in this presentation is that with multivariate data analysis, what we are accomplishing or what we're striving to obtain, striving for, is to calculate summary indices covering or summarizing the essential information in our process measurements. And this summary index is conceptually very, very similar to a stock index. Now we're going to play soccer. Here we see around 200 green points, and they reflect the body weight and body height of around 200 elite soccer players that were playing in the 2014 World Cup Championships that were held in Brazil. So somewhere here along the body height, 168, we will find the famous player Messi. This is a subset of all players, but it's still enough data points to, so to say, work out the basic messages. What we can do with multivariate data analysis is to create a summary index on how the body weight and body height changes among these elite or top level soccer players is changing. This summary in this index or summary variable is identified or indicated by the red dashed arrow. So there is no doubt that there is a relationship among body weight and body height among these top level soccer players. And generally it is so that with increasing body height, you have increasing body weight. So the summary index would be the red arrow. And then the interesting thing is that we can define a typical variation limit, a border of this model, you can say. And we here symbolize the border of the model using the black ellipse. When we are doing multivariate data analysis and calculating these summary variables, we usually define the model border to be positioned on a 95% level. So if you have fairly randomly distributed data, uniformly distributed data, you would expect that 95 points in 100 would be situated inside the model border and 5 points would be outside. So if you have around 200 soccer players, roughly 10 players should be outside the model border. So with MVDA, as we say for short, you can not only define summary indices summarizing the essential information in your data, but you can also define an envelope around the data points indicating the typical data distribution, a normal, a good, let's say, behavior. The interesting thing then comes when you're applying this data analytics model to future samples, and that is what we're going to discuss now in the next couple of slides. Let's say we would add the coordinates or the data, the measurement of a basketball player. And here we see what happens when we are adding body height and body weight of a very famous Chinese basketball player, Yao Ming. He was 141 centimeters tall and weighed around, sorry, he was 233 centimeters tall and weighed around 141 kilograms. There are several things you can see in this graph. First of all, the summary index is changing its orientation a little. The initial orientation of the summary variable is now indicated by the yellow arrow, and the updated or modified direction of this arrow is now indicated by the red dashed arrow. So there is a little rotation, you can say, of the direction of the summary variable following the introduction of the data points for the basketball player. The interesting thing is that it's obvious that the basketball player Yao Ming is very, very different from the soccer players. But the interesting thing is that the weight-height relationship for Yao Ming conforms with the weight-height relationship for the elite soccer players. Using a slightly statistical word, you would say that, or statistical jargon, you would say that the correlation structure among the weight and height variables is not changing when we are adding the basketball player to the dataset. So there is no doubt that Yao Ming is very different from the elite soccer players, but he still conforms with the model. And that is one typical behavior in data analytics when you're applying your model to future samples. You can have a deviation, but it's not modifying what we call the correlation structure. Now in the MVDA toolset in the SIMCA software, we then have a diagnostic tool called a contribution plot. And by double clicking on the green point for Yao Ming, we would then open up this contribution plot that would show in what way or how Yao Ming is deviating from the elite soccer player. And in this case, because the numerical values of the two bars, you can say, or the coefficients of the two variables, they are positive, it means that the deviation is towards a larger numerical value. So the interpretation from the inserted plot here, from the contribution plot, is that Yao Ming is both taller and heavier than the typical soccer player. But apart from that deviation, the introduction of the basketball player has no dramatic effect. Now, how to act or reason in this case depends on what you want to accomplish with the model. Now, if it is important for you to have a model on soccer players that can also be relevant for the basketball player, well, then the consequence of that sort of attitude or stance is that you have to fill the gap here with more data points. You will probably need more data points for shorter and lighter basketball players, starting to cover up this gap. And perhaps you need to add data points also for other types of athletes being professionals in other sports, for instance, volleyball. On the other hand, if all what you care about is a good model about top level soccer players, well, then you would conclude that this model is not appropriate for the basketball player because the basketball player is fundamentally different. Another type of deviation can occur also in data analytics. And now we have removed the coordinates or data points for the basketball player. And now we're watching how body height and body weight of a sumo wrestler is related to the distribution of the data points for the soccer players. Here we see data for the Hawaiian-born sumo wrestler Akebono Taro, who when he was at the peak of his career was weighing around 230 kilos or 240 kilos and was around 2 meters tall. And here we see a completely different behavior of the summer index. So here the yellow color is the original direction of the summer index dictated by the data for the elite soccer players. And now we see how this summary variable is changing its direction. It is rotating upon introducing the data for the sumo wrestler. So clearly the sumo wrestler has some more influence on the model, or it has a higher leverage if you're using a statistical term. And we may again use this diagnostic tool, the so-called contribution plot, for interpreting the deviation. And always the interpretation relates back to the average soccer player. I think I forgot to say that before. Here we can see the reason or the pattern in the variables indicating why and how the sumo wrestler is deviating from the model for the elite soccer players. We can see that the deviation is chiefly in the body weight, not so much in the body height. So the sumo wrestler is slightly taller than the typical soccer player, but not by much. But on the other hand, he is extremely much heavier than the typical soccer player. Another type of deviation can be where you have a point that is completely off the model for the soccer player. And now we have thrown in the coordinates for a gorilla. So according to the contribution plot, the gorilla is much shorter than the typical soccer player and much heavier. There is no way on earth that we can get a model for the soccer players to include the data points for the gorilla. If we want to have a good model for gorillas, we have to measure these measurements, body height and body weight, for more individuals, for more gorillas, and calculate a local model for the gorillas. And this is also sometimes something that you can come across when you're modeling process data. You will need to have more than one model. You will have to have a local model for one type of production condition and another local model for a second type of production condition. And one of the critical issues then going forward is figuring out when we are making our next measurements next week, which model is applicable. So summing up, going back a couple of slides, what the main objectives are of multivariate data analysis is to calculate summary indices. We are calculating the relationship between the variables, the body height and body weight. We are defining a normal region within which we typically are if the situation is quote unquote good. And then we're using that information to try to diagnose the future samples. If the future samples end up inside the black ellipse, well, then we know that tomorrow's production condition is in line with what was good conditions in the past. But if we have a deviation, we can then have different types of deviations. We can have a deviation that is very extreme, but it still conforms with the relationship among all our measured variables. We can have a deviation that is partly influencing the direction of our summary indices, that we may or may not be able to add into our model, and we may also have a data point that is fundamentally different, completely off the model. We know with this background, we are now going to look into what sort of values you can accomplish by applying multivariate data analysis to different types of data. And we will start off in an informal way by looking at a quick data analytics exercise on the betting odds for winning the Premiership in the UK for the season 2016-2017. So the data table we're looking into is a data set that was compiled July 1 in 2016. And every row here is then one of the 20 teams participating in the Premiership. In our language, inside the Semca software, every team would be an observation. And to describe the properties of the different teams, the potential for winning or the expectation for winning, we're looking at some variables that reflect the betting odds from a total of 26 betting firms. So in our standardized jargon in the Semca software, a row is an observation, in this case a team, and the column is a variable, either the betting odds or some properties that may or may not be related to the betting odds or may not be influencing the betting odds. And we are calling these the dependent variables, the Y variables. We have the UEFA ranking as of September 1, 2016. We have the capacity of the stadium, how many spectators it can accommodate, and we then have how expensive the team is. Now, I should also point out that the wage bill here is from the preceding season, because when the betting odds were compiled, the cost for each team was not available because the teams were not completely settled or defined. Now, if we are applying data analytics to this data table, there are different types of questions and different types of values that we can extract. And first of all, we would like to know who is a likely winner to bet on. Which teams should we not bet on? Which betting firms can be trusted in the sense that they have fairly similar odds profiles? And perhaps more importantly, is there some betting firm that we definitely should avoid because they have completely different opinions about who will win the championship? It can also be of relevance to look into the question whether there are some relationships between the betting odds and the UEFA ranking, and perhaps also correlation to the other responses. And conceptually or conceivably, if you would also compile this sort of data over time, let's say every second week or every month, what about the variability within time? We can also model such changes. What are the trends across time? In this case, it's just a one-time snapshot, and the data then relate to July 1. Now, when we are doing data analytics, we will try to present the results in terms of informative graphs. So when we are looking into the question which teams are favorites to win, when we're making a model only on the betting odds, we will be able to present a plot like this. And when we start to do a more detailed inspection, we will find out that there are some teams that are not seen as having a very large chance of winning, and those are found in the right-hand part. It's Bournemouth and Watford and West Bromwich and Burnley. They are not likely to win when you're summarizing the odds, the betting profiles. We can also make a little zoom in on the top favorites cluster, and when we zoom in, we will see that here we have Manchester City, Chelsea, Manchester United, Arsenal, Tottenham, and Liverpool. These are the 6 teams that are favorites to win. And it's interesting to see that as of today, about 3/4 into the season, about 75% of the matches are played. The top 6 teams are actually the top six teams according to the betting odds. So there is definitely some bearing of the odds set in July last year onto today's situation. Another thing that we may have observed already in this summary plot is that there is a deviation for Hull. So the question is now, is Hull a volleyball player? Hull, is it a basketball player? Is it a sumo wrestler? Or is it a gorilla? If I now use that analogy. So it's not easy and obvious for us to judge what sort of deviator Hull is just by looking at this plot. But by using this complementary plot, the so-called contribution plot, we will be able to diagnose how, why, if Hull is deviating. We will be given some guidance as to which sort of deviation is relevant for Hull, if it is a basketball player, a sumo wrestler, or a gorilla. In this case, the deviation is just in one single variable, and that is the net bet odds profile. And because the numerical value of the coefficient is positive, we understand that the deviation is because Hull has an unusually large odds. If the coefficient would have been negative, it would have been the inverse interpretation. We can then double click on this colored bar, the orange bar, for NetBet to have a follow-up and do what we call a drill down exercise in the Simca software. So here we see a line plot of all odds from NetBet just to corroborate that what we see in the model interpretation in terms of the model parameters also makes sense in the underlying real measurements or real odds data in this case. The next and perhaps more intriguing question that we can look into is if the odds firms, the betting firms, have the same rankings. And then we look in another type of plot. We call this plot a loading plot. So now every point is no longer a team, but every point is one of the betting firms. And the answer to the question is yes, to a large extent, these betting firms have the same rankings. There is some deviation for NetBet, but that one we have figured out already as being caused by the unusually high odds for Hull. We can now move on and look into complementary data analytics questions, and we now are able to invest with these complementary questions. We are trying to figure out if there is any relationship between the betting odds profiles and these so-called Y variables. Now we are looking into how they are relating to or depending on the UEFA ranking. And so now the distribution of the teams is based on how well the betting odds correlate or are related to the UEFA ranking. When going from left to right in the horizontal dimension, we have an increased UEFA ranking. So the teams that are not very highly ranked according to the UEFA ranking, they are found in the left-hand part, and teams that are very highly ranked according to the UEFA ranking are found in the right-hand part. In the vertical dimension, when going from the bottom to the top in this plot, we are looking at deviations between the betting odds and the UEFA ranking, and the further off we get from the zero line, the more pronounced the deviation is. Overall, there is a pretty strong relationship between the odds and the UEFA ranking. 88% of the variation in the betting odds profiles is correlated to the UEFA ranking. Only about 6.5% of the variability in the odds are not related to the FIFA ranking. So this is by far the most important scale. It is 88%, and the vertical dimension is just 6.5%. So we should not exaggerate the meaning of the vertical axis. We can then try to understand or figure out which betting firms follow the UEFA ranking, and then we can plot other diagnostic plots. And here we have, in a decreasing order of importance, how well the betting odds profiles are conforming to the UEFA ranking. So for Betfair Exchange, we have the largest conformity to the UEFA ranking, and the weakest relationship is for NetBet. We can also then look into where we have the deviations from the UEFA ranking and again present the sorted list. And here we see that the betting firm that has the strongest, let's say, opinion of its own, that is NetBet. followed by Betfair and Body Sport and Coral and so on in decreasing order, where we have then the deviations from the UEFA ranking. What about the correlations to the other responses, the stadium capacity and the salary costs of the teams? So here in the first plot we have the coefficients for the model that we just looked into, the relationship to the UEFA ranking. Here we have the relationship to the stadium capacity, and here we have the relationship to the wages. And we have highlighted the five strongest farms in the left-hand plot, and we can then see that also for the other responses we have similar odds dependencies. So the conclusion from this little exercise is that overall there are strong correlations among the betting farms. The little deviation is for NetBet. It has a different opinion about the chances for Hull to win the Premiership. The favorite teams have similar odds profiles across all the betting farms. The relationship with the UEFA ranking is pretty strong, and 88% of the odds variability is correlated with the UEFA ranking. And the favorite teams are large clubs with large stadiums, and they also have the most expensive players, and that is perhaps not, and of course not, any rocket science there. This is what we would expect, but it's still interesting to see that we are able to corroborate, perhaps, let's say, prejudices using these tools inside the Semca software. Now we're moving over to, let's say, an industrially more relevant application that deals with characterization of raw material coming into a pharmaceutical production process. And this is of importance because variation in raw material properties can be one reason for problems during manufacturing. And that sort of undesired variability can be because we have several suppliers of the same type of starting material. It can also be because there is batch-to-batch variability from the one and the same supplier of this starting material. So what we want to accomplish with the next couple of slides is just to shed some light on how you may use one of the data analytics engine in the Semca software to figure out if you have any variations in raw material qualities. And the data analytics engine that we have not named before or mentioned before is principal component analysis. So the data that we have relate to batches, incoming batches for almost 2 years of production for some pharmaceutical company, and the data are particle size distribution data. We see a plot of the original measurements here in the line plot to the right. There are in total around 250 variables corresponding to different intervals of particle sizes, and these particles range from 2.5 down here, 2.5 micrometer up to around 150 micrometer, and this size interval 2.5 to 150 is then divided into 250 bins or intervals. And also this bin size is non-linear, so when we have the smallest particles we also have the narrowest bins, and gradually as we move on towards larger and larger particle sizes, also the bins, the particle size intervals, increases. And the readout represents the number of particles in each bin, in each size interval. And the question is, can these particle size distribution curves be used for quality control of future batches? This is something that we will come into. What we see on this slide is something we will address in webinar 5. It deals with some pre-processing, and roughly you can say that usually you will be working with a pre-processing principle called scaling to unit variance, which I will explain in the next webinar what it means. But because these particle size distribution data are curve-like or spectral-like, we will work with another type of pre-processing, which we call the Pareto scaling. Pareto scaling is related to unit variance scaling, but it will not easen out or smoothen out changes that may be in the data when you have spectral data. Then we are applying one of the data analytics engines in the Simca software, the principal component analysis, to the data, and we are calculating two summary indices. Now think of the Dow Jones index and think of this initial trend chart where we had just one summary index. We are now having two summary indices, and these summary indices, using the jargon of data analytics, are called principal components. And these principal components explain more than 95% of the variability in the particle size distribution curves. We can then plot the plot here. This plot is now very similar to the soccer players, and it's also very similar to the plot where we were looking at the different teams in the Premiership model. So every point is now one row, and rows that are close together would then correspond to particle size distribution curves having similar profiles. We can also try to look at deviators, trying to find out if a point here is more similar to the basketball player, to the sumo wrestler, or the gorilla, using the contribution plot. And here we see an insertion of the so-called contribution plot for one of the deviations of 0.27, and we can interpret why certain points are different using that sort of tool set, but we will not dig into the details. Now, what do these components or these summary indices, summary variables mean? One way to investigate and explore what they mean consists of plotting the particle size distribution curves for spanning points. So here we have selected point number 5, batch number 5, and batch number 27. So we will try to understand what happens when we go from left to right in this plot. Here we see the particle size distribution curve for batch number 5, and the blue line is the particle size distribution curve for batch 27. So when we're going from left to right in this plot, we're going from the black distribution to the blue distribution. So going from left to right in the horizontal direction in the plot means we're transitioning from a high proportion of small particles to a relatively high proportion of large particles. In a similar way, we can also try to interpret the vertical dimension in this left-hand plot. And when we are doing that, we're plotting the particle size distribution curves for batch 43 and batch 30. So the particle size distribution curve for batch 43 is the blue line, and the particle size distribution curve for the batch number 30 is the black line. So when we're going from top to bottom, going from blue to left, blue to black, when we're going from top to bottom here, we're going from a comparatively flat distribution to a very sharp distribution at intermediately sized particle sizes. These are the interpretations. Now, the really interesting thing is that what I didn't tell you before is that this pharmaceutical company has 3 suppliers, 3 vendors of this starting material, and we have information on which supplier is relevant in the different batches. So when we now turn on the batch, when we are now turning on, you can say, the supplier information in terms of 3 colors. Green is the first supplier, blue is the second supplier, and red is the third supplier. We see really, really interesting things. The suppliers number 1 and number 3, the green and the red, they seem to be providing the most homogeneous and consistent starting material with very little quality variation. As opposed to this, we have the blue supplier, the second supplier, that has the largest variations in raw material quality. Now, here we are basing our quality control model, you can say, on 45 batches. But after a while, additional data became available, another 13 batches of particle size distribution measurements. And the interesting thing is if we can use this quality model for quality control of new batches. So we want to apply the existing model to prediction data, fresh data. And when we do that, we also have to specify inside the Simca software which batches we want to predict. And here we're just seeing a couple of screenshots of how to accomplish that. But that will also be illustrated in the demonstration. The really critical question is now, is the prediction set, the fresh batches, are those compatible with the model for the 45 initial batches? Inside the Simca software, there are several graphical tools that you can use to assess that question. In this case, the answer is yes, affirmative yes, because we see that the deviations from the model for the prediction set is on a similar magnitude. It's on a par compared with the deviation of the samples, with the deviations from the model of the samples making up the training set. Very quickly, we can say that the red dashed line symbolizes the model border. If you remember very early on, I put up a black ellipse structure around the soccer player. So that was the model border, the envelope. And the envelope in this case around the particle size distribution curves is symbolized by the red dashed line. So what we were hoping to see is something of this type, that the most of the deviation from the model for the prediction data is similar in size as the deviation of the training set samples from the model. So the question is now, are the suppliers, now that we know that the training set is applicable, representative to the test set, the really central question is, are the suppliers shipping consistent qualities? And we will now walk through the suppliers one by one. If we now look at the prediction set, we see that there are five batches from the first supplier, and because they are situated in this quality control chart, very similarly to where the green batches of the training set are situated, the conclusion is that yes, the first supplier, the green supplier, definitely is shipping consistent qualities with time. For the second supplier, the blue supplier, the conclusion is also yes, but the second supplier has a larger variability than the first supplier, but the variability for the batches featuring in the test set from this supplier is in line with the variability displayed by the batches in the training set from that supplier. Whereas the answer for the third supplier, very surprisingly, is no. There is a huge shift in qualities. We can see here that there was a very narrow or small variation in the particle size distribution curves for the red batches, or for the batches from the red supplier inside the training set. And now there is a real shift to the fresh batches coming from this supplier. So this is really critical information. It means that if a process operator or process engineer sees this sort of classification, he or she would understand that wow, now we cannot, with these new fresh batches coming from the red supplier, we cannot operate the process that we usually do when we have batches coming out from the red supplier. Because of this proximity to the reading where we have the batches from the blue supplier, the conclusion or the insight is that now we have to operate, when we get these let's say quote unquote red batches, we have to operate the process according to the principles for the quote unquote blue batches. So that is really vital information. Another thing that we may also want to understand is what is causing this shift for the red supplier. So we may want to compare properties of the initial batches from the third supplier to the fresh batches from the third supplier. And this is easy to accomplish in Simca. And the easiest way to accomplish that is to create a combination plot of the training set and the test set. So in the plot here, we're co-displaying all batches from the training set and the test set together. And then we're using this possibility of the Simca software to display the line plots of the raw data just to visualize the changes for the third supplier. So the black lines here, these are the early batches from the third supplier, and the red lines in this plot are the late fresh batches from the red supplier. And we can see that there is a significant shift in the shape of the particle size distribution curves. So the value here was that we were able to devise a reliable quality control model, and it uncovered that the fresh batches from one of the suppliers was very, very different compared with the earlier batches from that supplier. And the main reason being that the fresh batches comprised much higher proportions of larger particles. And we also understood that depending on where the fresh batches were classified in the quality control chart, different regimes, different modus, or different mechanisms, different operations of the process may be warranted. With this introduction to data analytics and these two data sets in mind, we are now moving into the software for conducting a demonstration of these two data sets.
We see here, I have prepared a little by starting up the Simca software solution. We see here the backstage where we have standard commands, new and open, and later on also save and print and close and so on and so forth. Inside the Simca software, you can run different types of projects depending on what type of data you are confronted with. We can have a regular project, that is the type of project we will run in this illustration. We can have batch projects if we have data arising from batch processes. We can run omics projects if we have omics type data, and we also have a spectroscopy entrance into the software if you are working with multivariate calibration. And how these different entrances work, we will touch upon in the upcoming webinars in this series. So we start with a regular project. We are going to import the data from this XLS file. We don't need the logos of the companies, they are still there. We need just the data. Here we see all the data in the import routine spreadsheet, and you can see that the Simca has pre-configured and colored some of the columns and the top row according to some information that it has come across in the data table. The first column is the primary identifier, that is what will be first thrown up in any plot. The second column is the name of the team, and that is the secondary ID, and that can also be used to understand the plots and enhance the information content of the plots that we are going to create. The top row is the name of the different betting firms, and to the far right here we then have these three Y variables, the UEFA ranking, the stadium capacity, and the wage bill. And these are so-called Y variables. If we are not saying anything, Simca will silently assume that all imported columns are of the X type. Apart from that, the issues pane reports no problems, so we can finish and give the project a name. I will overwrite a version of this project I did a couple of hours ago when I was rehearsing. So we have now imported the data. We can open up a table just viewing the data and just verify that everything went okay, everything worked in the import. We also can do statistics. We can do what we call work set statistics, where we get summary indices for all the columns in the data table. We have classical correlation matrix appearances and so on and so forth. That is needed and useful to just look at the properties of the data that we have just imported. The first data analytics model that we will do is the one looking into the betting the profiles of betting odds from the betting farms, and I will now ask for the two first summary indices to be computed. Here we have them, and we then make the first plot where each point is now one of the 20 teams. Instead of viewing let's say number from 1 to 20, we can configure so that we see the name of the team instead. So here we have the name. You can see that some of the names, Southampton and Bournemouth and Middlesbrough, are partly truncated. So we can increase the number of characters that we visualize from 10 to, let's say, 15, and then we see the full name. So here we see from left to right a decreasing chance or decreasing popularity, decreasing chance of winning the championship. Over here in the left-hand part, it is a little crowded because many of the favorite teams have very similar profiles of the betting odds, and we can then use a zoom tool to zoom in. And in the Simca software, we can zoom in as many steps as we want. And here we see on a very detailed level who are the favorites to win. And the favorite in July, at least, to win the title was Manchester City, followed by United, Arsenal, Chelsea, Tottenham, and Liverpool, in that order. But I must emphasize that these are very, very subtle differences between these teams. Overall, these 6 stand out as big favorites compared to all the rest of the teams. I can then also zoom out in equally many steps. Now here we have this deviation for Hull, and using a double click we can then create the plot that I called a contribution plot in the PowerPoint presentation, and try to figure out is, well, within quotation mark, quote unquote, is Hull a volleyball player, a basketball player, a sumo wrestler, or a gorilla, or a combination. And in this case it stands out in one variable, one betting firm, and that is the net bet. We can then also, as I told you, sorry for that, double click here to drill down to the raw data of the net bet company. So what we're doing is that the column here in the data table that is net bet, we are plotting the data for that column in a line plot. The other main type of data analytics model that you can accomplish using the Simca software, that is then to find what are the relationships between the betting firms and the different Y variables. And we will now make such a data analytics model to look at the UEFA ranking. You can of course do similar models also for stadium capacity and the wage bill, but we will exemplify this possibility using the UEFA ranking. I will again ask for the 2 first summary variables, and here is a plot where from left to right we have an increasing correlation to the UEFA ranking. So the teams to the right have the highest UEFA rankings, and when we go gradually from right to left, we get more and more decrease in the UEFA ranking. So all variations that occur in the horizontal dimension, that is variation in the betting firm odds that correlate with the UEFA ranking. And any variation in the vertical direction from bottom to top represents variability in the betting odds that is uncorrelated with the UEFA ranking. And in order to figure out what these variations are, we can start by looking into the variability in the betting odds firm that is correlated to the UEFA ranking. We don't really need the loading point for the UEFA ranking because it's always positive, so we can disconnect that part and just look at the information for the betting firms, and after that we can also size sort. So here in this plot, going from left to right, we see in decreasing order what is the correlation between that particular betting firm and the UEFA ranking. So the company that has the betting firms that have betting odds profiles most closely resembling the UEFA ranking are those that are to the left, BetF, Exchange, BetDAQ, Skybet, and so on and so forth in descending order. And similarly, you can also look at how the betting firms have betting odds profiles that do not correlate with the UEFA ranking. So here you can say that NetBet and Betfair and so on, these are the betting firms or betting companies that have the strongest opinion of their own, so to say, or at least betting odds profiles that are less correlated or less resembling the UEFA ranking. And whenever you have come up with a model of this type and you would like to communicate the results to colleagues or within the organization, you can always go back to this backstage and utilize the report generator. And the report generator will create the report, and the report is based on a series of placeholders that either encode a piece of text, a boilerplate text usually coming out of our documentation. It can also code, the placeholder can also code for plots and lists in a fixed order. And after a while you can also start to modify these templates and create your own favorite order of placeholders and your optimal template for your application. This is the start of an HTML compatible document, and basically you move down to the conclusions and start to type in your conclusions here. This report is stored within the project's file, but you can also open it up in a standalone situation outside the Simca software solution for further editing. How to work with the Simca report generator is also discussed in other webinars at our website.
So after this demo, we are now trying to sum up some of the messages conveyed by this presentation. So you can say that the Geometric suite that we are walking through has 6 software components, 6 software elements in it, and the basic objective of this toolset of softwares is to help our clients and users to see what others don't. Removing the names of the different software solutions and zooming in on the more applicability of this suite of softwares to address the different data analytics questions that may occur, we can say that with this set of softwares or data analytics solutions, we can look into the descriptive data analytics question to try to figure out what has happened. We can look into the diagnostic issue and figure out why a certain thing happened. Why did it happen? We can also look, you can say that these two questions, descriptive and diagnostics, they are a bit reactive in character, but we also have 2 more proactive stages. We have the predictive stage, where we try to understand what could happen in the future using statistical models and forecast techniques. And then we also have the prescriptive scenario, where we try to understand what should we do to make a certain thing happen, or perhaps even more importantly, what should we do to avoid a certain thing from happening? How should we avoid an issue to happen? And we are going to, in the upcoming webinars, address all these data analytics questions using relevant data sets and relevant softwares. So this is the last slide of today's presentation, and we want to emphasize that with the Geometric suite, the Sartorius Stedham Data Analytics Solutions wants to help our users to analyze their data, analyze the historical data, plan informative measurement campaigns, try to figure out and understand the golden nuggets in their data, how to capitalize on those golden nuggets, and thereby understand how to change a little and in those terms grow a lot. So having said that, I would like to round off this presentation. I thank you very much for your time and attention, and I hope to see you on board in the future in the upcoming webinars in this series aimed at exploiting the Geometric suite of data analytics solutions.